Welcome back to part 2. We are still in lesson 1.1 and 1.2, and we're going to pick up where we left off here with example 6. We were talking about where is the domain of this rational function. Now, I hope you can remember from Algebra 2, but if you look at this function right here, we talk about the domain, and because it's a rational function, I want to know where that denominator is 0, because it cannot be 0. It doesn't exist if I'm dividing by 0. Well, that would be where t equals -1 and 1, and it cannot equal -1 and 1. If I wanted to kind of graph this, you can graph this yourself. You can see that at -1 and at 1, you're going to have, hope you remember this, you have asymptotes. And so the graph is going to be doing something like this for this particular function. Okay, so it exists everywhere except -1 and 1. So let's talk about how we're going to write that. If we wanted to use the set builder notation, then we would say it's the set of all t such that t does not equal -1 and t does not equal 1, and all the other values of t are real numbers. Now, if I wanted to use interval notation, I can do that. I'm going to do this interval, the interval between them, and the interval there at the end. So this domain would be from -infinity up to -1, and it doesn't include the -1, so I have a parenthesis here. And it exists from -1 to 1. Again, I'm using parentheses, not brackets. And it exists from +1 to infinity. So I say 1 to infinity. Always parentheses with the infinities. Right? That is an example of giving me the domain. Another thing I would like you to do is to analyze functions. And we are going to do this so much, and we are going to keep adding to this list of different tools that you have to analyze. But we're going to get another one of our pieces of paper. I'm going to cut the next block off. And again, I'm going to write on it before I tape it down. And I'm going to use a pencil. I always like to do pencils when I do graphing. So quickly here, I'm going to sketch out an axis. I'm going to pause it for a minute while I write this down, and then you can pause it and draw it in just a minute. All right, let's talk about some of the things I put on this graph. You can see some of the little tick marks I made. All right, I went up 2, I went down -5, I went to the left. My x-axis goes from -6 over to 4. And my graph is going to start down here at -5, -4. It's going to go through -4. It's going to come up here to this hole. It's then going to hit here at -1.5. It's going to turn here at -3, and then it's going to go here, let's see, go like that, up through that's a +2.5. There we go. Okay, so let's analyze some of these pieces. All right, first of all, I would give you a picture like this, and I would say, what is the domain of this function? Well, the domain, you need to remember, is your x. Your range is your y. So when I'm asking you what is the x, the domain, that means you look at your graph and you look at the x values. Well, the least x value I have here is -5. And then it goes up to -3. There's a hole there. It doesn't exist there. And then from -3, it exists everywhere to infinity. So, and again, we prefer the interval notation. So there's a dot there at -5. It includes -5, goes up to -3, and there's a hole there, which means I need a parenthesis. It doesn't include it. And then it picks up on the other side at -3 and goes all the way to infinity. We have no idea where it stops. There's a little arrow there on the end. Okay? Let's talk about the range. The range are the y values. So look at your y values of this function. The lowest y value, the least one, is right here at -4. And let's go up. -4, it exists everywhere here. Oh, look, there's a hole there at 2, but the function still exists at 2 over here. So that hole does not apply to the range, because of the function on this end keeps on increasing. So we're going to say the range just is from -4 to infinity. Always have a parenthesis, but remember -4 down here is a closed circle, so it gets a bracket. Let's talk about your intercepts. Review these. Y-intercept is where x is 0. Your x-intercept is where your y is 0. So if I look where my x is 0, my x is 0 right here, and that's at that one spot, -3. So you can either tell me the y-intercept is -3, or you can say the y-intercept is at 0, -3. And you give me that point. Okay, that's an important differentiation. That's not an interval notation, that's a point. Let's do the x-intercepts, where y is 0. Well, I've marked those with some dots, right? So I'm going to say the x-intercept is at -4, 0. Where's the next one? -1.5, 0. And you can make that 1.5 if you want. 2.5, 0. Okay, and again, please remember that these are points and these are intervals. It's important that you remember that, because they will get to the point where they look alike, because you're using the parentheses and the commas, but you need to remember which are the points and which are the intervals. All right, now let's talk about some symmetry. I'm going to go ahead, tape that down so I don't lose that anymore. All right, symmetry of functions. Typically when you do the symmetry, you can tell by looking at them, but also you will need to prove it algebraically. So let's talk about what this means. The symmetry of a function is when it reflects around a line, an axis, or point. Now, here we've reached the last part of our notes sheet here. We are only going to be concerned right now with 3 types of symmetry. I am aware that you can draw a function that is symmetrical, that is not have one of these 3 types, but these are the only 3 types we are going to work with right now. So I want you to pause for a minute. We're going to draw some. If you would like to pause and then come back and sketch them in. So go ahead and pause it right now so that you can sketch these out, and then we'll talk about them when you come back. The x-axis one is a parabola that is facing to the right, obviously. The y-axis is facing down, and the origin symmetry spins around a point here at the origin. Now, I chose to draw parabolas that have, obviously, the vertex is on one of the axes. This one happens to be at the origin. This is on the y-axis. But I want to talk about the graphs themselves. If a graph is symmetrical to the x-axis, then when you graph it, you can essentially fold it in half on the x-axis and you get a symmetrical picture. Now, if you imagine what's happening here, you have the same x, but do you see how your y's are different? One would be positive, one would be negative. Here you have the same x, but it has the same y's, but one is positive, one is negative. So you can remember this function right here, that the x stays the same and the y will be negative. When you have y-axis symmetry, you have a graph that is symmetrical to the y-axis, and therefore, when you fold it in half on the y-axis, you get the same graph. But look at what happens here. The x values will be different. You know, this is going to have the same y value, but the x will be a negative x, and this would be the same positive x. So here, the negative goes with the x value. When you have origin symmetry, that means that you spin this graph or around the origin like a pinwheel. You can go clockwise or counterclockwise, but you're going to get the same graph. It just spins around the center there. And it doesn't matter. They both are going to give you the negative of the other when you spin it. Now I want to talk about the function notation for these, because if you are just going to evaluate this at f of x, then that would equal the negative y value. So the negative function value. This is how you're going to be able to prove this algebraically. If you look at the function, is that equal to the negative of the function? And if so, we say that it has x-axis symmetry. Look at this point. If you evaluate the function at negative x, does that equal y, which is just f of x? So if you plug in negative x, everywhere there's an x in your function, in your equation, does that eventually, after you algebraically work that out, does it give you the same function? If it does, it is symmetrical to the y-axis. The origin symmetry, if you evaluate this at negative x, that would give you the negative function value. So you can algebraically prove it with these steps down on the bottom. Okay, let me tape this down real quick. Also, there's one more thing we need to talk about. We call y-axis symmetry even functions. And we call origin symmetry odd functions. And I always remember that because origin is an O and odd. So I can keep those together in my mind. Function. There's not a nice name for x-axis symmetry, but we do talk about even and odd functions as having y-axis symmetry and origin symmetry. Okay, when you come to class, I will answer any questions that you have about this lesson, and we will be working the assignment together. Thank you.